Okay, welcome everyone. It's a pleasure to have with us, even remotely, Almog Yalinewich from across the seas in Toronto. Almog did his BA at the Open University in high school. Then, during the army time, did a master's at Ben Gurion and his PhD, parallel to me, at the Hebrew University with Am Sari. He's now a postdoc at the Institut Canadien d'Astrophysique Théorique. And he'll talk to us about a new conservation law for surface explosions.
Right. So before I start, I want to say thank you for the invitation. So I'm going to be talking about, as Ofik said, I'm going to present a new conservation law for surface explosions. And just so that you will get a sense of what I'm talking about, it's basically analyzing events that are demonstrated by this experiment. So here you see basically a sand pit and a bullet fired directly into it. So you can already see, you can just make out a crater forming at the center and the debris scattering all around it. And in essence, what I'll be describing is a mathematical model that describes the evolution of the shock wave and the debris resulting from such an explosion or release or impact. So the structure of the talk is as follows. So first, we're going to start by presenting a number of astrophysical scenarios that at first glance seem to have no connection between them. Then I'll argue that they can all be all these different processes can be described by the same mechanism and with the same analytic solution. Then I'm going to describe how you obtain this analytic solution and all the math that's involved. And then I'll show how you can use the solution. So it's like once you have the solution, it's like a master key that opens many locks, and you can obtain many insights about these processes. So moving on to the astrophysical scenarios. So I think that as you know, every so often, Earth is bombarded by asteroids and meteorites from outer space. And the thing that the aftermath and the thing that persists for longest are impact craters. I try to find an impact crater in Israel, but there doesn't seem to be any, or at least if there was, it's been eroded. And the closest one I was able to find was in Jabal Waqf S1 in Jordan. But there are many craters like this all around the world. And in the context of in the study of these craters, what people mostly are interested in is relating the size of the crater to the properties of the impact, velocity, the mass, so forth. Now, when you go back in time to the beginning of the solar system, then the collisions become bigger and more violent. And actually, it's the common paradigm now in regard to planet formation is that terrestrial planets like the Earth, and Mars, Venus, and Mercury, is that they don't form monolithically like stars. What happens instead is that in the protoplanetary disk, you form many small planetesimals, and they collide with each other and merge. And this is how you grow. You go to planet sizes that are comparable to the Earth or even larger than the Earth. And these collisions can change. They can leave more than just the mark that they leave is more than just a crater. They can change the orbital parameters of the target. They can change the spin. They can also generate a debris stream that can cause occultation. And there's one claim that such a stream has been observed in an exoplanet system. In the context of the Earth, one of these collisions was implicated in the formation of the Moon. And the thing that I've been working mostly on, I've dedicated most of my time studying, is the atmospheric mass law. So the idea is that you have such a collision, and what it does is knock out some of the gas that's surrounding the planet. And this is of course important for the study for the prospect of life in finding life in other planets. Finally, I want to present this oddball. So this is a peculiar supernova called IPTF 14HLS. So this is a supernova that was that erupted and was detected in 2014. And as you can see from the light curve to the right, it's considerably brighter and considerably longer than a normal supernova. Now, you might be tempted to say, well, maybe supernovae just come in all shapes and sizes, so what's the big deal? So the issue here is that most supernovae, the reason that they last for as long as they do, a few months, is because they're mostly powered by radioactive products. So nickel 56 that decays into cobalt and so forth. And these elements have rather short lifetimes. So whatever is powering this transient, IPF14 HLS, can't be radioactive decay. So already we're posed with a question, and this is, what is the source of energy of this transient? Now, one suggestion, idea that's been proposed is that it's essentially powered by a jet. So we know that whenever you have compact objects like black holes or neutron stars, and they're fed very rapidly by a mass source, they tend to launch relativistic jets. And we have a mathematical theory to describe it, and there are observations of this process. But this would require that somehow you would get a compact object like a neutron star into the center of a star. So how do you get this to happen? So one idea is that you basically invoke an exotic evolution track. So the idea is as follows: you start with a massive binary. One of the stars explodes, turns into a supernova. Now, this supposedly would have happened millions of years ago, so it's not something. This is a stage you could not have seen. And then the companion evolves, turns into a giant. Sweeps the neutron star into the envelope, and at this point you have a common envelope evolution. And at some point, the neutron star spirals in, starts secreting material from the dense degenerate core, launches a jet. This jet blows up the star and continues to pump energy into the ejector. And supposedly this goes on for two years or as long as it does, and provides all the energy. So this is an alternative energy source to radioactive decay, and this idea has been proposed in Sokka and Gilkey's 2018. Now, that's not the last peculiarity about this transient. So
Can you go back to that
yes.
two slides back?
Yes.
So yeah, so this is IPTF event.
Yes.
I have two questions. First,
yes.
Was it a single unique event, or was there more than a single event like that?
Event. It's in what do you mean, a single event in one sense? You're saying was it the only one bright as bright as this?
Not just as bright. I mean, you're showing us some light curve, right?
Yes.
Which lasts for over a year. Which
yeah,
shows
close to 2 years.
Well, roughly 2 years.
Yeah.
Which shows several distinct peaks.
Right.
And each peak is of the order of 100 days or so.
Right.
Are there any other sources that show somewhat similar light curve to that?
So I think I know there are events that are as bright, but I don't think so the combination of being bright and being prolonged is something that's unique to this supernova. I think there are other that are just as bright but not as long.
Okay. And my second question.
Yes.
I mean, since you're seeing here several distinct peaks, right? I mean, in the model that basically you are describing, you're saying that possibly the source of energy is not radiative decay, but essentially it's the gravitational energy, right, of the neutron star that falls into the gravitational potential, and then results in throwing some of the energy outwards. Then what could be the origin of these distinct peaks in this model?
So you can when you talk in the study of neutron stars, you find all sorts of timescales. For example, this could be precession. This could be, for example, maybe precession timescales. If you have a misalignment between the magnetic field and the rotation axis, this could be the rate that it wobbles. So there are long timescales. So I don't think it's entirely solved, but one effect could be one of these. It could be one of these precession timescales, or some secular effect.
And why do you see distinct peaks?
So it could be that if let's see, where would you see distinct peaks? It could be a geometrical effect, or it could be. So we know, even when we look at normal, right? When you look at accreting neutron stars, regular accreting neutron stars, you know that they go through cycles. They go through duty cycles. So it could be that we're seeing something similar to that. Right? You go to high soft state and then low hard state. It could be that what we think is analogous to this, but I don't think it's fully solved.
Well, that would not be a common envelope, right?
No, so by this time the common envelope at this point have already been dispersed. So the claim is that what we're seeing now is already after the envelope has been ejected.
So what is the picture then? Maybe I missed the picture. So what is the picture of what produces that?
So the idea here is that you have the neutron star spirals in. When it makes it all the way to the core, then it starts secreting material from the core, and then it launches jet, because the core is much denser than the rest of the star. And this release of energy is what gives rise to the supernova, and it ejects the envelope.
What's a TZO?
Thorne-Zhitkov object. So this is an object where you have basically a neutron star that's embedded inside a star, but they sort of coexist. It doesn't destroy the star. But the star would appear peculiar because, right, you would generate more luminosity than a regular star of the same mass. So it's an exotic kind of object, and until recently it was only speculative. But now there's a work by another student here at the University of Toronto that claimed that they actually found candidates. But again, it's a very rare kind of object, even if it does exist.
Okay, so I still don't fully understand. So you're arguing that these different distinct peaks are coming from different jets?
No, so it could be that the intensity of the. So again, it's not something that's been fully explained, but you do see variability in, like, it's not out of the question, because you do see variability on long time scales when you look at the neutron stars.
Well,
So
but here you seem to have fluctuations, in time.
Right.
You have one relatively long peak, and then there is a shorter and brighter peak.
Right.
And then we're seeing sort of a half a peak, and then there is a peak which has a very sharp decay.
Right.
So they don't seem to have the same origin, or they don't seem to resemble each other in terms of the light curve. It seems to be quite distinct from each other.
Right. But maybe so it could be. But I think even if you try to explain this, you would only need two different frequencies to explain. So it's not like you have. Right. The difference here is not orders of magnitude. We're talking about factor of 2 in duration and in amplitude. And also when you look at so again, we don't know the origin of the duty cycle in regular accreting neutron stars. So it's not out of the question. So again, I don't have the answer for what's producing this, but I'm just saying similar phenomena have been observed in neutron stars.
Like that time scale? Hundreds of days?
For not hundreds of days, but let's see, for a duty cycle could take of the order of weeks or days, if I remember correctly.
Okay.
So again, yeah, it's not so again the model doesn't explain all the features that's been observed in the supernova. Well, the properties that it does explain is where the extra energy is coming from. But there are fine-tuned details that it doesn't explain. I don't think there's any model that explains all the time variability that we are observing.
If you look at the first peak and the last peak, they look very different, right? I mean, the last peak, for example, has a reasonably shallow rise and a very steep decline.
The last one here?
Yeah. It rises, right? Reasonably slowly. Takes, I don't know, like a few tens of days, but then it just decays over, very difficult to say, but no more than a few days.
Right.
And the first peak seems that the rise time and the decay time seems to be quite the same time scale.
Right.
So I find it hard to believe that this is the same mechanism that produced both of them.
Well, you also see that there's a decline here in the energy that's not observed on the other side. Like the decline here is much. The decline here is on the at late time is also much much more moderate than this.
But that could just be that could be radioactive decay that was just buried before by higher signal.
What do you mean buried? You can't bury. You generate all the radioactive elements the moment that you explode the star. There's no more nuclear reactions going on afterwards. So whatever you produced would have decayed in the early months.
Is there spectrographic analysis of these light curves as well, or you just have the integrated power?
So people looked at the people have looked at the elemental abundance there, but I don't remember all the properties there. But I don't remember anything too peculiar about the composition.
Okay.
So again, I don't have a model that explains all the variability that we're observing in this light curve.
What was the trigger for this observation?
So what do you mean the trigger? So IPTF is an all-sky mission.
Right. No, but for this particular event, right? Days since discovery. What was this discovery? Was it just something random, or was there something that happened to the source that caused its discovery?
So it was a brightening. It was a brightening of the source.
So there was some brightening of the source that occurred at t equal to 0.
Right, because what you're seeing here, this is an order of magnitude more than regular supernova.
Right.
Already here. So yeah, it wasn't part of any other campaign. It was just part of an all-sky survey.
Okay.
So again, this is not even the last quirk about this transient. So it turns out that even 60 years before the event, there was another outburst from the same source. Again, something that's very very bright, not as bright as the terminal supernova, but comparable to other supernovae. Unfortunately, because it's 1954, there's no light curve. There's just one measurement of, just one report of the magnitude and the sun period where it's been observed. So for about a month, the luminosity was comparable to 10 to the 41 ergs per second. Now, according to, if we follow this interpretation, and so 2014 was the year where the neutron star made it all the way to the center. If we go back 60 years into the past, it must have been further away from the center, so closer to the edge. Now, if there was any energy release at this time, then you would get a surface explosion. I have show here a simulation of what such an explosion would look like. So you can see. So maybe I should also mention, so these are calculations done with my computer code. And if you can see the polygons here, it's not a bug, it's a feature. So what's special about our code is that it uses a moving mesh. So what you're seeing here are actually the computational cells. So you can see that you have a shockwave that's moving inward and ejecta that is expelled. So if every fluid element is being shocked and eventually is expelled out of the basin. And
what's the scale for that?
So again, this is dimensionless. So I'll talk a little bit later about the right, because what I'm simulating here is just the atmosphere. So this is just some power law intensity, and this is the and this is at some arbitrary distance. So
what's the physics? The real question is about the physical model. So
right.
You're assuming that there, at some depth inside the neutron star, there is explosion that occurs?
No, so it's not. Sorry, so it's not inside the neutron star. It's inside the giant. So the neutron star is releasing an amount of energy inside the envelope of a giant.
Well, I thought you said that the envelope is long gone.
No, so it's long gone in 2014, but this is in 1954.
Oh, I see. Okay.
So this is decades before.
Well, but then the explosion did not destroy the envelope?
No.
Okay.
So this is an excellent question, actually, but to show that even if you inject an amount of energy that's sufficient to destroy the envelope, it won't destroy the envelope, because basically because you invest the energy in an inefficient way, right? So if you have an amount of energy and you want to dissociate and you want to destroy a star, then you want to give each fluid element the smallest amount of energy that you need to unbind it. But what this does is it gives this, when you deposit all the energy at a single point, you give a lot of energy to a small mass and you launch it at a very high velocity, and then the shockwave decelerates too fast to destroy the entire star. So a star can even, if you inject the explosion very close to the edge, it can survive an explosion with more energy than its binding energy. So it's the same explosion that would have destroyed it at the center, if you put it at the edge, it would only make a dent.
If this is the envelope, I'm still not sure to understand the setup that you're using.
Right.
So the physical pictures, you have this envelope which become a common envelope, right? And
right.
the neutron star is now entered the envelope.
Right.
Rotate inside, and then what? And then at a certain point something explodes.
And at a certain point, yeah, it releases a certain amount of energy. Now,
but it's somewhere close to the surface, right?
Yes.
Now, why is the surface so sharp? I mean, I would imagine that in that case, then it would be very gradual wind. But here in the simulation, it seems that you're starting with a very sharp.
Well, I'm assuming that. So if you have an adiabatic atmosphere, then you do have a sharp end.
Well, but you have a neutron star that spirals inward.
Right.
So it will definitely produce a wind.
Right. So here I'm not simulating the whole thing. I'm just simulating one. So here I'm just injecting. I'm not. The neutron star is not even in this simulation. I'm just injecting a certain amount of energy into an atmosphere. Now, in our model, we assume that this is what happens. You just inject, the neutron star passes through the envelope, and at some arbitrary point, it releases all the energy. But in fact, you would get the same behavior even if the neutron star is releasing the energy gradually, a large amount of energy continuously inside the star.
Now,
So
what does the neutron star to release the energy?
that's a good question, and this is the what I'm discussing in the next slide. So neutron stars are known to release or at least they've been observed to release a huge amount of energy. So for starters, we know that there are neutron stars that emit more than Eddington luminosity, not by a little bit. Right? In this example, this ULX M82X2 is continuously emitting energy, emitting 2 to 3 orders of magnitude more than Eddington luminosity. And this alone, if you just do the same thing as the neutron star passes inside the neutron common envelope, you would get the same behavior as if you release all the energy instantaneously. And in addition to that, neutron star, quiescent neutron stars that are constantly accreting material are known to produce these flares. So every so often, seemingly at random, their brightness would increase by considerable fraction. So here I'm showing just one example. So we don't fully understand why these events happen, but all that I'm claiming is that neutron stars are perfectly, at least observationally from observation, are perfectly capable of producing a very high luminosity, which is all you need for this model.
Well, but that's because they form accretion disks.
Sorry?
That's because you have a lot of accretion of material.
Well, you have a lot of accretion over on this side. This thing is accreting at sub-Eddington, and it still produces these flares. This is a different system. So yeah, again, all you need, right? And I think that it's also important to say that in order to produce the amount of energy required to produce the transient, you only need to accrete a very small fraction of mass from the companion. As I'll show later. Maybe I can also talk about this a little bit now. So the reason this could be very bright is because the what happens in a regular supernova is that you have this explosion, but by the time it becomes transparent and photons can meet, you have adiabatic cooling because you have to wait for all the material to expand. Here, because you interact with a small amount of mass, then you get much less adiabatic cooling. So even a very small amount of energy can produce a very bright flare. So after I've presented all these different problems, I want to claim that you can describe all of these shockwaves, all of these processes by a single analytic solution that's based on self-similarity. If you're not familiar with self-similarity, I think the figure to the right shows, so what you see here to the right are simulations of a point explosion. So this is a much simpler problem than cratering, than the surface explosions that I've been talking about. So what they've done here is they just injected energy into an infinite uniform medium and followed the shock wave. And if you look at this, you will see that the profiles are very similar to one another. But mathematically, you can also express this idea mathematically. And the way that you express it is by saying, well, if I know the profiles at one time and I want to produce the profiles at a different time, all I have to do is just stretch them and compress them by the proper amounts. And this also means that each one of these profiles can be described by just a single universal profile that is stretched or contracted by the proper amounts to produce the profiles at different times. And this is a kind of symmetry that we can use to simplify the full problem. And originally, this idea was used right after the Second World War, when there were rumors about the new weapons, the new atomic weapon that the Americans used. But at the time, nobody knew the yield or the amount of energy released in this explosion. And this is something that most of world powers wanted. It's a piece of information most world powers wanted to get their hands on. And eventually, the way that it was figured out was by at some point the Americans released footage of the explosion. And this is just one frame. Basically, what you see in this footage, you see the fireball grows, and according to the rate which the fireball grew, you could figure out what amount of energy was injected. And this is basically was just using energy conservation. So if you just use energy conservation and you assume that, and you make some simple assumption, you can find that and assuming that the explosion is self-similar, you find that the shock wave has to increase with time as t to the 2/5, and this is a very famous set of Taylor law. And if you fit the shock trajectory to this answer, you can find you find the p-factor, you can actually reproduce the energy. But unfortunately, this model doesn't work for surface explosions. And the reason it doesn't is because the energy that's available to push the shock constantly diminishes, because as we've seen, matter flows out of the basin. Now to describe this, because I'm trying to develop an analytic model, I'll have to make some sacrifices. I'll have to simplify the problem for as much as possible. Hopefully, after I've obtained a solution, I'll be able to take into account these effects, to incorporate these effects back. So regardless of the medium, I'll always assume an ideal gas equation of state, and assume that regardless of even if these are explosions in the soil, I'll neglect material strength, I'll neglect radiative cooling, and also gravity. But it turns out that this is not enough. This is still a complicated problem because in the most general case, it's a 3D problem. If you assume symmetry, then maybe you can reduce it to 2 dimensions, but it's still too complicated. So now I'm going to make the final leap. I'm going to use the so-called impulsive piston approximation. So in this case, I'm going to forget about the classical problem that you can think about is something is an asteroid hitting the ground. So instead, I'm going to think about a wafer, a thin and infinitely wide wafer that hits a semi-infinite plane. And because of this is slab symmetric one-dimensional problem. So it's the one-dimensional equivalent of an asteroid impact. And you can see to the right, you can see simulations of what the shockwave looks like. You can see that as it expands, it tends to this universal profile. And the question is, the question that I'll be trying to answer is, how does this shockwave decelerate with time? The interior of the shockwave. So to answer this question, we have to essentially solve the hydrodynamic equation. So the hydrodynamic equations in slab symmetry in one dimension are given here. So these are essentially the conservation of mass, momentum, and entropy. Now you could say, well, wait, why entropy, right? Because we have a very strong shock wave and entropy is not conserved there. But because I'm only trying to describe the interior of the shock, then I can assume that entropy is conserved. Essentially what I'm saying is that all the entropy is generated when a fluid element is shocked. Afterwards, the entropy remains the same. And here I'm taking into account the equation of state of an ideal gas. And here to the left, is the definition of speed of sound. So what I'll be doing is I'll replace the pressure with the speed of sound. The reason I'm doing this is because it's going to make the analysis, the algebra is simpler when you do this. Now to further simplify so maybe I should say, the hydrodynamic equations are partial differential equations. So we have three different profiles. So the density, the material velocity, and the speed of sound. And we have two independent variables, the time and the position. But what self-similarity will help us do is reduce this to ordinary differential equations. So instead of depending on two independent variables, we'll have just one independent variable. And the way that we do this is by noting that because this problem doesn't have any length scale or time scale, then the trajectory has to be some power law of the time. And likewise, the velocity would be some power law of the position, and with this index. Now these two are related, but delta is just easier to work with. Now, even before we proceed, we can already place constraints on what delta should be. So delta should be in between this range, right? If you conserve energy, right, that's the fastest we can go, then delta is equal to -1/2. And if we conserve momentum, then would be -1. Now, conservation of momentum, you can understand in analogy to the snowplow phase in supernova remnants. Essentially, the phase where every bit of thermal energy that you produce is just radiated away immediately. So all that's left is just the momentum. Now, according to the same logic, the only important position, right? If x is the absolute position, then the only thing that's important for this solution is the relative position relative to the shock. So everything is going to depend on this parameter, on this chi parameter. That's the ratio between the absolute position and the position of the shock front. And using these variables, I can express all these dimensional parameters as a product of dimensional part, a simple dimensional part, and a dimensionless part, dimensionless function. Now, you might already see that I've made a weird choice. So here I just express this as a single function, but here I'm expressing it as a function, as a product of chi and v. I could say, well, this is just more overhead. Like I could have absorbed this into v. But it turns out that if you do this, if you express the function in this way, in this particular form, then you can simplify them even further. And I'll show exactly why I made this choice in 2 more slides.
Can I
Yeah.
stop you for a second? I'm sorry, I'm a little bit slow on that. So you're trying to express, right, the properties of the explosion that occurs just below the envelope, right?
Yes. So again, I'm assuming that it's so close to the surface that you can assume that it's flat. The
Right.
surface is flat.
So you have a surface, right, and then you have
Yes.
here's no explosion.
Yes.
Why is it true? But then again, why is it true to assume 1D model?
That's an excellent question. That's an excellent question. So what I'll show is how to solve the one-dimensional model, and then there is a way to generalize the results to 3D. So the idea here is that we reduce the problem up to the point that we get something that's simple enough to solve, and then I'll argue that there is a way to generalize the result that you get to 3D. But it's an excellent question. But basically, the idea here is that what my strategy is to just reduce the complexity of the problem until you end up with something, and then move back using the insight that you obtain to generalize it to more cases. But this is an excellent question, and I have I'll discuss this in a few more slides. So if you can bear with me, you'll get the answer to your question. So you take these variables, you substitute them into the hydrodynamic equations, you get this monstrosity. Now you could say, well, you've only made things worse, right? We had equations that look quite elegant, and now we have this mess. But again, the benefit here is that instead of depending on two variables, these equations just depend on a single independent variable. So again, these are just a system of ODEs. But thanks to this substitution, we can go a step further. We can reduce everything to a single ODE. But the price here is that instead of depending on position, we just relate the dimensionless speed of sound to the dimensionless velocity. Now, the right-hand side is also, again, is a mess, but it's a mess that only depends on C, V, and the two constants, gamma and delta, that we're trying to find. And all we need to do now to solve it is to integrate it. But to integrate it, we need boundary conditions. So on one side, the boundary conditions are very straightforward to get. This is just the strong shock conditions, so the Rankine-Hugoniot conditions. So just some function of the adiabatic index. The more interesting boundary conditions are on the other side. And to understand them, we need to think about what happens to a fluid element. So imagine a fluid element that gets shocked. At first, it tries to follow the shock front, but the shock front is moving faster. It's moving away from it. And at some point, this fluid element decelerates, stops for a moment, and then it starts accelerating in the opposite direction. And as it does, it cools down and moves. So it's moving faster and faster and expanding as it does. So the velocity increases, the speed of sound decreases, and at some point it's going to cross the point of no return, a point where nothing that happens to this fluid element will be able to propagate all the way back to the shock. And this is the sonic point. And mathematically, this point manifests itself as a singularity. So from the condition that the curve passes smoothly through the singularity, you get the other condition. So all that's left is just to integrate. And now we've basically reduced the problem to a shooting method, to a shooting problem. Basically, we have to start from here and find the correct parameter for which the trajectory will hit this point. And this is what it looks like. Now it's a little bit complicated, but I'll try to explain as best I can what's happening here. So the red point here is the sonic point. The X on the left is the shock front. And you can see that for different choices, if I start from here and I numerically integrate the ODE to the shock front, if I choose different values for delta, then I hit different spots. And there's only one value of delta for which you hit the right point. So this is how you determine delta. Now, why does this look like this? Right, we have a very strange integration contour, right? We start from here, then we move all the way to the right, then we re-emerge from the left and we move again. Why does this happen? This is because of the way that I defined, right? So I made this strange substitution earlier, and the benefit of it was that I was able to reduce the three partial differential equations to a single ordinary differential equation. But the price that I had to pay was that I'm introducing coordinate singularity. So it's a singularity that doesn't exist in reality. It's just due to the way that I define things. So let's think about what happens at x equals 0, at the initial point of contact between the impactor and the target. So what's happening there? The answer is nothing special. You'll have some finite velocity and some finite speed of sound. The problem is that chi goes to 0 there. So this means that capital V and capital C, the dimensionless quantity, have to diverge. And they have different signs on different sides. So this is why you jump from here to here, and you continue the integration from there. And the ratio, also the ratio between them is conserved. So the Mach number remains the same. And this is basically, and the way that we do it technically is we integrate from here to some very distant point. We note the slope, and then we continue the integration with the same slope from some arbitrary large point on this side. So what I've shown here is a method to determine this delta, this deceleration parameter of the shock.
Just for orientation,
yes.
The plot on the right top is a zoom
Is a
in.
zoom in. Yes, it's the
to
zoom in.
left.
Yes, I should have. Yes, thanks for.
And the line that's blue on the left turns into the line that's green on the right on the final resolution.
Well, it's all of them. It's just that it's too small to see the dispersion between them.
So you go from the red point
Yeah.
to the right and bottom. You flip back over to the top,
Yes.
and then that's why the slope on the right top is going from left to right, downwards.
Yeah, it's always going down, downward and to the right.
You try to catch exactly, hit the.
Yeah, so you try to hit. Yeah, it's like a shoot. Yeah, it's like a shooting problem. Right? You try to choose the right parameter to hit the shock front.
Okay, and this parameter seems like an analytic number.
Well, for this choice, this is for a particular choice of gamma, but for different values of you're correct. There is one value of gamma for which you can solve this analytically, but for an arbitrary choice, you'll just get an arbitrary number. So there's no as far as I know, there's no analytic expression that relates gamma to delta. So for different choices of gamma, you will get different values for delta. And this is also something that's different from the set of Taylor solution. In the set of Taylor solution, you have a power law index that doesn't care about the equation of state. But you can have all the equation of state matters is for the prefactor. But here we see that choosing a different equation of state would yield a different power law index. Now, on the one hand, at very low values of gamma, we see that we basically reproduce momentum conservation. So this behaves the same way as if you had radiative cooling. And the reason for that is that low gamma means a very large number of degrees of freedom. And if gamma is equal to unity, then you have an infinite number of degrees of freedom. So whenever you generate heat, all this heat goes into this infinite number of degrees of freedom that don't increase the energy. So it's the same. So qualitatively, it behaves the same as if you had radiative cooling. So this is why you conserve momentum. On the other side,
can you again explain the difference between the solution that you're presenting and the Sedov solution?
Yes. So so in the Sedov solution, throughout the evolution, you always conserve the energy. The energy that's enclosed inside the shock region is always the same.
Right.
In this solution, some of the energy, so again, the energy in the universe as a whole is always the same, but the energy that's available to push the shock is only the energy that's contained between the shock front and the sonic point. And energy continuously flows through the sonic point. So the energy that's available to push the shock diminishes all the time, according to some power law. And this is why you get, right, because if you had conservation of energy, then you would be at delta would be just minus 0.5.
Right. So basically, you can think of it as a Sedov solution with a change of energy.
Yes. So if you have it's like a Sedov solution with an energy sink.
It's an energy sink. Sorry, yeah, that's the right word. Right.
Yes, but
sink is at a constant rate.
It's not a constant. It's some power law.
The power law.
Yeah, it's some power law in time. So it's also the amount of energy that you drain is also scales with the energy.
Okay.
Yeah, so you can think about it, but again, the crux of the problem is finding the so if you know at what rate you drain the energy, that you solve the problem. But the crux of the problem is determining this quantity. How much energy do you drain all the time? And this is essentially determined by the sonic point. This is why the sonic point is so important, because if you understand what goes on in there, you can tell how fast you drain the energy. Okay, so explain what's happening on the lower end. When you go to the upper end, when you take the analytic limit of gamma goes to infinity, you find. So I was expecting to get in analogy, I was naively expecting to get energy conservation, right? Because we saw that on one end you get momentum conservation. We know that there's an upper limit on the other side, but actually you don't find that. You find that the curve levels off at some arbitrary number, some 0.57, which I don't have any intuition about. So you get very close to energy conservation, but not quite. I don't have a good explanation for why this happens. Now, we in essence found that this solution is in essence represents some sort of fractal conservation law. So, right, in analogy to, right, if we had energy conservation, we'd expect the velocity to scale as m to the minus half. If we had momentum conservation, we'd have velocity scale as m to the minus 1. we find in this solution for reasonable values of gamma, you would be somewhere around 0.2 now we have intuition for what energy conservation represent, right? With some sort of symmetry in the Hamiltonian, and the same for the momentum. But this is kind of strange if you think about it. So I want to offer some, if not a full explanation, then at least a geometric interpretation of what this power law represents. So let's think about fractals for a moment. So here's a very famous fractal called Sierpinski's triangle. And what you do here is that you start with a filled triangle, you divide it into four smaller equilateral triangles, and you cut out the middle. And then you do the same for these triangles. And once you've done this in an infinite number of times, you end up with something that by definition doesn't have any area. The area is identically 0. And you can also get the same shape by starting with this line and continuously deforming a line. So if you try to describe this measure this with something that has length, then you would need an infinite length to reproduce the same shape. But of course, this thing does have some sort of a dimension, but it's somewhere in between. And you can understand this quantity in a similar way. So think about the shock and imagine that the shock doubles in size. When it doubles in size, the energy diminishes by a certain fraction. Every time that you double in size, the energy diminishes by a certain fraction, determined by the solid point. The momentum increases by a certain fraction. So by the time that you've done this an infinite number of times, you would have something where the energy is 0, the momentum is infinite, and this quantity remains finite. Now that we had this insight, so I think we're slowly coming back to the thing that was bothering you. So now I'm going to deal with some of the now that we have an insight, I'll try to argue that we can incorporate some of the effects that I've neglected so far. So one of them is the equation of state. So right, if you have an explosion close to the edge of a star, then you can use an ideal gas equation of state. That's a good approximation. But if you're considering a meteor impact on soil, then you can argue, well, the soil is not an ideal gas. How can you use this assumption? So what I argue is that indeed, under the conditions that are familiar to us, the ground is not an ideal gas. But when people do experiments, shock experiments, and they take so here is an example for used silica. So this is the most of what soil is made of. You see that at low velocities, you get complicated behavior. The speed of sound, the shock velocity can go up, it can go down. You have shock, we have phase transition, you have whatnot. But at some point, you get that the shock wave increases, the shock velocity increases linearly with the particle velocity, which is the same thing that you would expect from an ideal gas. And more than that, you can use this relation, the Houguenot relation, for an ideal gas to calibrate what the effective gamma would be. So if you do this, for example, for metals, you might find that the effective gamma could be more than 2 or more than 3. But again, because I only care about what happens here, then this is why I argue you can use, because the Houguenot curve is essentially the same, this is why I argue you can use an ideal gas equation of state.
Can you go back? What exactly are you showing in this plot?
So these are experiments. These are gas gun experiments. So if you're not familiar with these experiments, basically when you want to find the equation of state of some mineral or metal, you take 2 slices of them, you put one as a target, you put one in on top of a bullet, and you put it in a gas gun, and you smash them together. So you can use the barrel. You can measure the barrel velocity, and this is how you get the particle velocity. And you can also measure the if you have a graded surface, then the way that you do it is you have a target in the shape, you have a stepped target, and you fire lasers at both sides, and you measure the time difference between the shock arrival at different points. So you can measure independently the material velocity and the shock velocity.
But this is here talking about solids, right?
Yes.
But what you're describing, right, is an explosion into the remaining envelope of the star, and there are no solid.
Right. So this is what I said. I said if you want to describe the star, then for a star you can use an ideal gas. But my claim is that the solution is more general. You can even use the same solution to describe explosion in the soil.
well, I guess you would get an equation of state of it's not necessarily ideal gas.
Right, but
It will be some gas, right? But I'm not
right.
sure how is
No,
that
so
what you're showing
so
here.
what I'm claiming is that because the Hugoniot curve is very similar, then this is why I'm justifying my choice of using an basically what I'm arguing is that you can use an ideal gas. I'm trying to justify the choice of an ideal gas even when the target is not made up of an ideal gas. And the claim here, what I'm claiming is that when the shock is strong enough, all materials behave similar to an ideal gas. And more than that, I can use the Hugoniot curve to calibrate an effective value for gamma. So does this answer your question?
Semi. Well, what's the expected temperature of the ambient gas?
In what scenario?
Well, the scenario that you're considering, right? That of an explosion inside an envelope.
So there well, I'll get to that later, but basically the idea is in my scenario, release of the order of 10 to the 48 ergs at a distance of 10 solar radii from the edge of a star that's about 100 solar radius. This radius is about 100 solar radii. I didn't calculate the temperature inside the explosion, but I did calculate. What I calculated was just the observed temperature. So yeah, it's an easy exercise to do. Just that I haven't done it. I haven't calculated what the temperature inside would be, but it's not relativistic. This is
it's not a 367. Okay, I'll go on.
Okay.
And what's the temperature for the soil meteor?
So you can get 10 to the 4, 10 to the 5 degrees, depending on the material. You can get very high. So it's a very simple calculation, right? You know that for the Earth, for example, things collide at about 10, 20 kilometers per second. And if you have a metal-dominated shock, you just take this velocity and multiply this by the right. It's just mv squared, and you get a very high temperature. So it's 10 to the nothing remains. If you have a very strong impact, everything vaporizes basically. So now we're coming to the topic of geometry. So so far, as Asaf mentioned earlier, everything that I've done so far is just for a one-dimensional case, but reality is 3 dimensions. How can I generalize the solution? So I argue that the main difference that changes when you go from 1 dimension to 3 dimensions is that the way that the swept up mass scales with distance. So in the 1-dimensional case, the mass increases linearly with distance, while for the 3-dimensional case, it increases cubically with distance. And this is something that you can incorporate into the 1-dimensional model by considering, instead of a uniform density, considering an ambient density that scales at some power law with distance. So you can make this substitution and it doesn't break self-similarity. And you can see how of course here is beta, which is the power law index of velocity as a function of mass for different values of the adiabatic index and for omega. And what you can see here is that once you set gamma, the adiabatic index, and you change omega, this power law hardly changes. It's very weakly dependent on this omega. So you do see that there's some dependence, but the lines here are almost vertical.
Where do you expect the adiabatic index of 3 or higher?
So again, the reason I'm taking these into account is because because what I've shown earlier, when you calibrate this model for metals, for example, when you consider shocks in metals, which is something that we did consider because of planetary collisions, then you can get. So again, it won't be the same as an adiabatic index, but in our model, as far as the Hugoniot curve is concerned, metals behave as though they're ideal gases with a very high adiabatic index.
Yeah, that I can understand, but what about this, the environment that you're interested in, right? The envelope of a star.
Yeah, but again, it's not the only application. So for a star, it would probably be somewhere over here.
Right.
Yeah, but my whole claim to fame is that the same model can describe not just explosions in star, but also impacts on planetary collisions. So this is why I care about very high indices. So the idea is that you can use the same model, and at most, all you have to change is just this adiabatic. So from you want to apply to a different setting. So this is why. But I agree, for any stellar application, you will probably only care about what happens on the left, here on the left side.
Yeah, but if you want to explain it, but then again, I don't fully understand your model, because if you want to explain, for example, meteorite collision,
yes,
then the source of energy would be at the surface of, the boundary between, let's say, the solid surface and the atmosphere, which you can take as a vacuum if you want.
yes.
But I thought you were presenting a model in which the source of the explosion was below the surface.
So an asteroid impact is the same as a subterranean explosion, where the depth is comparable to the size of the impactor. So if you have a meteorite that's 100 meters in diameter, it's the same as if you release the same amount of energy at a depth of 100 meters. Assuming the densities of the impactor and target are the same.
Well, is there a simple way of seeing that?
Yes. Well, I don't know about simple, but you can think about it in the following way. So imagine that you have a collision between, right? You have this impactor. Let's assume that it's much smaller than the size of the because we're talking about meteorites, then it's much smaller than the size of the target. So let's say 100 meters. This is something that's going to make a splash, but it's not. You can consider the surface to be flat. So imagine that this thing hits the ground at the very early times, when the distance that the shock travel is much smaller than the size of the impactor. You basically have a Riemann problem. You basically have a planar shock that's propagating. And
you have it at later times as well.
Sorry?
You have it at later times as well.
No, but at later times it's not. But at first you can neglect geometry. You can't neglect geometry at later times.
Okay.
The idea here is that so at very early times you won't convert. At very early times you can think about the impactor as continuously pumping momentum and energy into the ground. And because it's continuously pumping, then you don't converge to my solution. And you have to wait until the shockwave is at a distance comparable to the impactor before you converge to the self-similar solution that I presented. And because self-similar solutions forget all the information about what created them except for the conserved quantities, then you would get the same, qualitatively you would get the same behavior if you took the same amount of energy and you deposited it at a depth that's comparable to the size of the impactor.
Okay.
Right, because what the initial shockwave does is it sends most of the energy to this depth before you converge to my self-similar solution.
Well, I can see that only if they have the same density.
That's what I said. Assuming that they have the same density, and if it's not, then I think if they have different densities, then this would be multiplied by the square root of the density to match the impedances. But for planetary collisions, the density is always almost the same. Like it's not going to be orders of magnitude different. Maybe asteroids tend to be slightly more metal rich, so they're slightly denser. But again, we're talking about a difference between 2 grams per cubic centimeter and 3 grams per cubic centimeter. It's not going to be. It's not going to make a huge difference.
Almog, how many slides do you have left?
I'm just now getting to the application, so I can run through them fast. How much time do I have?
Aim for 5 to 10.
Okay, so I think I can do it in 5 to 10. Right. So the first wait, are there any more questions, or if not, I'll just move on. Okay, so now that we have the size, the scaling relation for the crater, for the surface explosion, we can estimate the scaling of the size of the impact, the size of the crater. And the idea here is that you deposit a certain amount of energy into the ground. We consider ourselves with scales that are much larger than the length scales that are much larger than the size of the impactor. And the idea here is that this shockwave is going to propagate into the ground, and at some point it's going to stop, because at some point the debris that it launches are going to be too slow to leave the rim of the crater. They're basically going to fall back inside. And you can show that this condition is comparable, is similar to the condition that the acceleration of the shock is comparable to the gravitational acceleration. And when you do a little bit of math, you find this scaling relation between. So on the left-hand side, we have the ratio between the size of the and the size of the impactor. And on the right-hand side, you find you have the ratio between the velocity of the impact squared, so the impact velocity squared, and the product of Ri, the radius of the impactor, and the g, the gravitational acceleration. And when you compare this to experiments, you find that so these are experiments in the blew explosives or shot bullets directly into water and measured the size of the biggest bubble. And you find some relation between the size, here some straight quantity that they use to measure the size of the crater and the strength of the impactor. And I find this scaling relation. And when you do the analysis that I've using the method that I described, when you do the same analysis using the same quantity, calibrated equation of state for adiabatic index for water, you find that the theoretical slope is 0.643 instead of 0.648. So extremely close to the experimental results. This is something that, as far as I have seen, no one was able to reproduce in other work.
Can you explain again what was shown in this plot here, Ray? Yeah?
So again, so here they show the results of different experiments where they either blew explosives close to the surface of water, or they fired bullets into a surface of water, and what they were trying to measure was the biggest size of a bubble. And so here what they do is essentially, so here they present a dimensionless measure of the volume of the crater, and this is the measure of the strength of the impactor, or how strong the impact was. So here, V is the volume of the impact, volume of the crater. Rho is the density of water. M is the mass of the impactor. Delta here is the density of the impactor. G is gravitational acceleration, and U is what I called VI here. So it's the velocity of the impactor.
So if you have an impactor which is bigger, then you get a lesser crater?
No, it's going down, right? The slope is going down. So if you have, right, if U is larger, then it's going down. You have, right? So you climb up because it's in the denominator. It's in the denominator. So larger U means you're going to the left, and you have a larger crater.
Okay.
What's the effective gamma for, I guess, for water in this case?
So it's slightly, let's see, what I remember is the effective delta. Delta would be 0.6. So it's, yeah, so it's slightly more than, somewhere it's close to 2. Because what we were getting is that it's closer to the effective delta in this case would be 0.6 instead of 0.67. Oh, sorry, I'm running ahead of myself. So I think I'll skip this because it's less interesting. Oh, sorry. Any more questions about scaling and cratering? Another signature that we can calculate is something called the ejector blanket. So this is something you would get basically because what a crater does is excavate a certain amount of material, and then it scatters this material around the crater. So if you look close to the crater but not inside the crater, you would see that the ground level is slightly elevated compared to before the crater. And this is because of all this material that used to be inside where the crater is now. And there's a way to estimate to get this shape, the ejector blanket, from the scaling relation that I've shown before. And the idea here is that each fluid element gets a certain velocity, and this velocity defines a range that you can get to. You can throw this fluid element to. And since we know how velocity scales with mass, then we can find the scaling law between the radius and the mass. Now, if we assume that the now the surface density would just be the mass divided by r squared, and if the unshocked density is the same for this material, then this would also be the scaling law for the height. So using this argument, we find a scaling relation between the height of this ejector blanket and the distance. And this beta, we know that it's somewhere in between -1 and 1/2. So this means that this expression would be somewhere in between -2.5 and 3. And many craters on the moon exhibit this, show the slope. So this is one example from one of the largest ones from the Oriental Basin. And you can see that the slope is roughly within this range. Now, when you do this, I will just mention that when you do this for the Earth, you get something steeper. And this is because of air drag. Air drag tends to make things steeper because you have more material that's landing closer to the crater. If you remember, about 7 years ago, there was a bolide, so an asteroid that burned up in the atmosphere above Chelyabinsk in Russia, and it caused quite a bit of damage to people living nearby. And when people looked at the reports of damage, they found that the reports of damage per 1,000 people scaled as r to the -2.4. And this is very similar to the way that the pressure is expected to scale from simulations, from numerical simulations, which is r to the -2.6. Now, using our theory, again, without calibrating for the right equation of state for air, we find that P should go like r to the -2.7. So again, this is relatively very close to what's been observed and simulated. Again, we also see when in simulations of atmospheric mass loss, so even when you don't consider a flat ground, so here you get the same scaling. So here we have simulations where I collided an impactor with a target, and I measured the velocity at the antipodal point. So on the other side of the planet, and you can see that the way that the velocity scales with the radius is v goes like r to the -2, which is the same thing that you would expect from our calculations. And you can also use this our scaling law to estimate how much atmospheric mass loss, how much from the atmosphere would be lost due to a collision. So the idea is that you have something that hits the ground, it launches a shock, and it's moving faster than the escape velocity, and it launches a shockwave that slowly decelerates. At some radius, it's going to be the velocity is going to drop below the escape velocity, and you will lose all the gas column above this circle. And the relative mass loss is going to scale like the radius squared, and this goes like m to the 2/3. And when people did this simulation numerically, and they took into account a complicated equation of state and gravity and all the effects we've neglected, they essentially get the same scaling law. Now, finally, coming back to the topic of IPTF HLS HLS and its 1954 precursor. So the idea that we had in mind was that you had some neutral star on some eccentric orbit, and at some point it dipped into the envelope of the companion. And at this point, you deposit all the energy. So the model, we just used the same model that was used by Soka and Gilkis of an 80 solar mass progenitor star for the companion, 100 solar radii, and we just assumed that for simplicity that so these are just arbitrary values that we chose, that the deposition of energy happened about 10 solar radii below the surface, and that it released about 10 to the 48 ergs. So this is roughly what you would get if if you multiply the Eddington luminosity by the Keplerian time at this distance. Now we did simulations of how such a shockwave would propagate in a graded atmosphere, and we find this value for the convective atmosphere and this value for the slope of the trajectory for a radiative atmosphere. And both of these are actually well-defined, both are well-described by the same scaling law between velocity and mass. And you can just convert them with this relation over here. How much time do I have left?
You should aim to finish.
Okay, so maybe I'll just talk about the luminosity. So to translate this to luminosity, to translate the shockwave to an observed signal, we had to estimate how much luminous energy would be emitted. And this is not straightforward to get from the hydrodynamics alone, because the shockwave deposits a certain amount of energy in the atmosphere, but this energy is not free to reach the observer. It's going to expand and up to some point where radiation can decouple from matter. And in this process, there's going to be some adiabatic cooling. So you end up seeing less than the amount of energy originally deposited in each fluid element. And the condition for decoupling is when diffusion is faster than the fluid velocity. And this is roughly given by the condition that the optical depth is comparable to C over V. And this would give you...
What were the axes on this plot?
Oh, so this is just distance normalized by... So this is distance normalized by the depth of the explosion. So everything's scaled here. You can see the flow of... what I show here is the pressure.
So it's distance from the explosion and height.
Yes. So using this condition, we can plot the light curve, and we find that roughly at the time scale of about one week, 1 month, we find that the energy, the luminosity, the bolometric luminosity is 10 to the 41, which is roughly what was observed in 1954. Now I'll skip this ahead. You can also, just assuming that you have black body emission, you can estimate what the temperature is, and we find that throughout most of the evolution, the temperature is, in the early stages, is much too high to be observed from Earth, but roughly at the same time scale of weeks to months, we find that the temperature drops to the visible range, where most of the photons would be released in the visible range, and that it can be detected from Earth, because if the energy is too high, you can't detect it from Earth. So again, we did choose the parameters kind of arbitrary, but the fact that we can match both the luminosity and the temperature makes it encourages us and makes us optimistic about the plausibility of this model. So to conclude, I've presented the universal model for surface explosions, and I've demonstrated this can be used for a very wide range of problems, ranging from planetary collisions to from planetary collisions to stellar explosions. So with this, I'll conclude, and I'll take any more questions if there are still any.
Yeah, I have another question.
Yes.
You're showing the picture from the Trinity experiment, right?
Yes.
Atom bomb, and you're arguing that there is a lot of energy that is escaping outside the surface, and that's why the classical setup solution is not going to work for that.
Well, it's not gonna describe the shock that propagates through the ground. It's going to describe well the shock that propagates in the air.
Yeah. Okay, I agree. Now, how is that different than the setup that you have for, let's say, a meteorite explosion or a meteorite heat?
So the shock that propagates through the air is going to be very similar. So the set of Taylor solution would be adequate in describing the shockwave through the air. But what I care about is the shock that goes through the ground, because because this has more in the context of atmospheric mass loss. This is the right. If you have an explosion, so there are two problems. If you care about the atmospheric mass loss, then there's a limit to how much mass you can lose through the shock that's propagating in the air. And one problem is that you have a finite scale height. So at some point once you expand to distances larger than the scale height, then it starts decaying much faster. And the second thing is that I think you can only lose, at most you can lose all the material that's above the tangent plane. And what we care about in the context of giant collisions are collisions that can get rid of most of the atmosphere. So in order to get rid of a large portion of the atmosphere, you have to have a shock that can traverse most of the planet. So this has to be a shock that's moving through the ground.
Okay. Well, in that case, the planar symmetry that you're assuming would no longer hold, right?
The what? The what symmetry?
Linear symmetry that you're assuming.
Right, but yeah, but that's the beauty of it, because what I've shown here is that even when you don't have planar symmetry, even when you have a shockwave that's propagating through a sphere, you still reproduce the scaling law that I predicted. So again, this is from simulations. This is from numerical simulations that I ran. And the argument here is that when you describe the solution in terms of Lagrangian variables, so velocity and mass, it almost doesn't care about the geometry.
Okay, thank you.
Any more questions? Any of the students have questions? Students or postdocs?
While finding the slopes at the sonic point, why didn't you use L'Hopital's rule instead of using shooting method, which looks complicated?
Well, because one of the problems is that, right, if you look at the okay, so in principle you could use L'Hopital's rule, but then the thing is you don't know what the slope should be, right? So what L'Hopital's rule give you is the slope at the sonic point as a function of delta, but I don't know delta offhand, right? This is what I'm trying to figure out, right? So what I know is I have this integration. I know what the boundary conditions will be here. I know what they're supposed to be here, and that's all I have to go on. So you can't estimate delta based on local properties. You have to somehow connect these two data points.
Yeah, okay.
So we do use it to estimate the slope, right? Because for numerical reasons, you can't start exactly at the sonic point. You have to move slightly to the side. So we estimate what happens slightly to the side by using L'Hopital's rule.
Yeah.
Anyone else? Okay. If not, let's thank the speaker again.
Okay. So
I've stopped the